Hi everybody, so we're in section 4.5, continuing our discussion on derivatives in business and economics. So this is the section on average cost. So if the cost of producing a quantity Q is C of Q, then we say the average cost, A of Q, of producing quantity Q is given by A of Q equals cost over quantity. So C of Q over Q. All right, so if I'm selling 100 products for $500, right, I would have 100 products being sold for $500. Then I take 500 over 100, that would be $5 per product, right, per unit. Okay, and so that's what the average cost is giving us, is cost per unit sold. All right. So a company has a cost function. C of Q is that function where Q is the number of cases of product they produce. If 100 cases are produced, find the average cost per case. Okay, so if they produce 100 cases, then the total cost would be C of 100. So that's 0.01 times 100 cubed minus 0.6 times 100 squared plus 13 times 100 plus 1,000, which we can find to be $6,300. That would be our total cost. So the average cost, of 100 would be total cost over quantity, which of course is the 100. So that's going to be $63 per case. So that would be our average cost. Now, average cost can actually be related to marginal cost. So I want to take a look at the average cost function, and let's find the critical points of this function. So we need to take the derivative, set it equal to 0, and find what happens there. So we're going to do a prime of q. Now this formula, c of q over q, this is a quotient, right? A function of q over a function of q. So we need to use the quotient rule. So that's going to be low d high minus high d low, which derivative of q is 1, so we don't need to write that, over low squared. And then to find critical points, we set that equal to 0. Now let's simplify this down. Multiply the q squared across. Anything times 0 is still 0. So we get q times c prime of q minus c of q equals 0. Add the c of q across. So we get q times c prime equals c. And then divide both sides by q. So we get c prime equals c over q. So at the critical points of the average cost function, an interesting relationship has shown up here, because this right-hand side, that is the average cost function, right? So that's this function right here. And this function on the left, that's the marginal cost, right? C prime is the marginal cost of the product. So at a critical point, we can say that marginal cost equals average cost. So an interesting relationship we have. Now we can look at the relationship between the average cost and the marginal cost. Okay, so let's look at this example. So a total cost function in thousands of dollars is given by C of q equals q cubed minus 6q squared plus 15q, where q is in thousands and going from 0 to 5. Okay, so first it wants us to graph the average cost function, and then we'll determine analytically where it is minimized, and then graph the marginal cost function on the same axes, and then show that the minimum average cost equals marginal cost. Okay, so before we get to the graph, because I want to do that on Desmos, let's just find the average cost first. So for part A, let's just find average cost, and then we'll graph it in a minute. So that's going to be q cubed minus 6q squared plus 15q all over q. Okay, divide that factor of q out, so we're left with q squared minus 6q plus 15. Okay, so it is parabolic. And then determine analytically the exact value of q at which it is minimized. Okay, so to determine where it's minimized, we need to find its minimum, right? So we take the derivative, set it equal to 0, find the critical points, test the critical points. Okay, so that same process that we've been going through. So we're going to get a prime of q equals, that's 2q minus 6. Set that equal to 0. That's going to give us q equal to 3. Okay, and we can test right to the left and to the right of 3. Just plug in something smaller than 3, you get a negative. Something bigger than 3, you get a positive. Okay, so this is in fact a minimum. So we can say the minimum occurs at q equals 3. Okay. And then part C, again, we'll look at the graphs in just a second. But for this one, we need the marginal cost function. Okay, so let's go take a look at the original and take its derivative, right? Because that's marginal cost. So C prime of q, that is 3q squared minus 12q plus 15. So notice this one's also parabolic. Okay. So again, we'll graph that in just a minute. But first, let's show that at the minimum average cost equals marginal cost. So for this one, we're looking at the minimum. So again, at q equals 3. So at q equals 3, the average cost, a of 3, that's going to be 3 squared minus 6 times 3 plus 15, which is 6. And marginal cost at 3, that's going to be 3 times 3 squared minus 12 times 3 plus 15. And that one also equals 6. So we can say thus average cost equals marginal cost at q equals 3. So at that minimum average cost, we do get average cost being equal to marginal cost. Okay? So now let's go ahead and look at this graphically. So let's switch over to Desmos. And then let's graph these functions. So Desmos, I'm going to use x instead of q. But we get our average cost function is, so it's q, so x squared minus 6x plus 15. Okay, and then we want to only be from 0 to 5. So I'm going to go ahead and restrict that. There we go. So there's our function for average cost on the interval from 0 to 5. And now let's get the marginal cost on here. So marginal cost we saw was 3q squared minus 12q plus 15. So that's y equals 3x squared minus 12x plus 15. And we'll go ahead and also include that restriction from 0 to 5. There we go. So now if we look at what's happening here, so again the red graph is the average cost, the blue graph is the marginal cost, and look at the relationship that we found right here at the point 3, 6, right, at the minimum value of average cost and marginal cost, that is where they intersect, right? They're equal to each other. Okay, so that's exactly the relationship that we just saw, but now of course we see it graphically. All right, so that's the end of 4.5. So let's go ahead and move forward into section 4.6. So our last section is chapter 4, talking about elasticity of demand. So elasticity of demand gives us a numerical measure of the sensitivity of demand to price changes. But the practical meaning of this value depends on the specific product. So when we're talking about elasticity of demand, we're talking about how responsive a product is depending on how big of a price change has occurred. So for example, if we are increasing the price of candy bars, for example, right, and I raise the price of a candy bar by a few cents, the demand for those candy bars is probably not going to go down very much, right, because I only raised it a few cents. Whereas if I raise the price of a candy bar by $5, a huge price increase results in probably a large drop in demand. People would stop buying the candy bars. So this is what we're looking at, is how sensitive is a product to a change in price. Generally, products that are not very sensitive to price changes are like essential products. One great example of this is gas prices, right? Notice that gas prices continually go up and up and up, and yet we keep buying gas because it's an essential product. So the demand is not going to drop very much for gasoline, even as price increases. So we would say that this product, gasoline, is very inelastic. So we say inelastic because it's not changing very much. The demand doesn't change. And typically that's what we see with essential products like food and things like that. Where you might get something that does have a significant change in demand would be like non-essential products or products that have a lot of alternatives, right? So like for flat screen TVs, for example, if I am looking to buy a flat screen TV and I go to the store and I see there's one here for $1,000, right? And maybe I'm feeling inclined to buy that. I go the next time and its price has been increased to $1,500, right? And I say, well, I didn't really need a flat screen TV, or I really didn't need that one. Maybe I'll find a cheaper alternative. So the demand for the product is going to drop if the price goes up because people don't need it as much, right? Or people are willing to find alternatives. So that product would be considered elastic because there is a lot of change in demand. Now, when we're talking about elasticity, we have to have a common way of measuring elasticity, and this is where this comes in. We're going to consider a price increase of 1%. So we're working with percentages here instead of just dollar amounts, because if I'm working with just pure dollar amounts, raising the price of a candy bar by $5 is a huge price increase on a candy bar, right? But raising the price of a car by $5 is not very much at all, right? I wouldn't be, if I'm willing to pay, $20,000 for a car, I'm not gonna, scoff at a price of $20,005, right? So the price increase really depends on what the product is. Okay, so instead of working with a specific dollar amount, we're working with a percentage. So say we're increasing the price by 1% of whatever its corresponding value is. So then to find elasticity of demand, so how sensitive demand is to these price changes, we use this formula. So we have E equals the absolute value of price over quantity times derivative of quantity with respect to price. So it's the absolute value of P over Q times dQ dP. Okay. What this value tells us, so the value E tells us the elasticity. This tells us increasing the price by 1% causes a drop of E% in demand. Okay, so increasing the price by 1% causes a drop of E%. If E is greater than 1, the demand is elastic. If E is between 0 and 1, the demand is inelastic. And if you're wondering what happens when E is less than 0, well, it'll never be less than 0 because it's an absolute value, right? It'll never be negative. So let's go ahead and take a look at an example. So the demand curve for a product is given by Q equals 1,000 minus 2P squared, where P is the price. Find the elasticity at P equals 10 and P equals 15 and interpret your answers. Okay, so we need to get the derivative first, right? That's going to be used in our formula. So dq dp equals derivative of this function, that's 0 minus 4p to the first. So that's just negative 4p. Okay. Then let's look at, so when p equals 10, the derivative, so dq dp evaluated at p equals 10, that's negative 40. And q at this price would be 1,000 minus 2 times 10 squared. So 1,000 minus 200, which is 800. So our value for E is going to be absolute value of, of 10, right, P over Q, 10 over 800 times negative 40. Alright, so that gives us negative 400 over 800. So that's absolute value of negative 1/2, which of course is just 1/2. Okay, and we'll make conclusions about that in just a second. But let's go ahead and find the 15 case first. So here's our first one. And then when P equals 15, the derivative evaluated at 15 is going to be negative 4 times 15, so that's negative 60. And Q is going to be 1,000 minus 2 times 15 squared. 15 squared is 225, times 2 is 550. 450. And then 1,000 minus 450 is 550. Okay, so let's find the E value here. So that is absolute value of P over Q, so 15 over 550, times the derivative, so negative 60. Okay, and if we find this one out, we'll find that it gives us a value of about 1.64, right, as a decimal. So if we look at these results and interpret what these mean. So let's look at the case when P is 10 first. So when P equals 10, when the price is $10, elasticity is 1/2. So we can say at $10, a 1% price increase results in a 1/2 or 0.5% demand decrease. So demand is inelastic. Okay, and again, that would be because the value was less than 1. Okay, so we got E was 0.5 or 1/2. So we have a 1% price increase results in a 0.5% demand decrease. Okay, and then the other case we had at $15, a 1% price increase results in a 1.64% demand decrease. Okay, so this is a little more disproportionate, right? So we're getting a larger demand decrease for a 1% price increase. So demand is elastic. So this is an important distinction to make. Notice this is the same product, but we got at a certain price it was inelastic, and at a different price it was elastic. And why is this? Well, if you think about it, if I'm charging $10 for a product, and then I decide to raise my prices by 1%, maybe my customers are a little more inclined to continue buying it because it was just 1% off of $10. But if I'm already charging $15 for the product, maybe I'm kind of pushing them a little bit beyond what they're comfortable with already, and then I go and raise the price 1%, a lot more of them are going to stop buying my product. Okay, because their willingness to buy it goes down as the price goes up. Okay, so you can get different values for elasticity at different prices. And in fact, as price goes up, so does elasticity, right? Because the more they're paying, the less inclined they are to pay that additional 1% on top of it. Okay, so let's look now at a special relationship that we have between elasticity of demand and revenue. Okay, so let's look at the function. Revenue is price times quantity. Let's find the critical points of revenue. So it's kind of similar to what we did in the last section with average cost. So derivative of revenue with respect to price. So that's going to be this function here, that's a product. So we're going to have to use a product rule. So first times derivative of the second plus second times derivative of the first. Okay, and derivative of p with respect to p, that's just 1. Okay, so this is just p dq dp plus q. And then to find critical points, we set it equal to 0. So go ahead and subtract the q over. So that's p times derivative of q equals negative q. And then I'm going to actually divide both sides of this by q. So that's going to give us p over q times dq dp equals negative 1. And you might be able to see where I'm going with this. Now if I take the absolute value of both sides, I get absolute value of p over q times dq dp equals absolute value of negative 1 is 1. So what do we have here on the left-hand side? Well, this is e. And then the right-hand side we have 1. So it turns out the critical points of the revenue function occur when elasticity is equal to 1. So the critical points of revenue occur when E is equal to 1. So what that means, what it tells us, is that if we want to find, for example, maximum revenue of a product, we need to look at the elasticity. We need to find the price that allows the elasticity to be equal to 1, and that's where we're actually going to be maximizing our revenue. So pretty interesting relationship there. So let's take a look at this example. So let's start with part A. So 300 units of wool are sold when price is $10. When the price of wool is raised by $1, what is the effect on revenue if quantity sold drops by 10 units? Wool's demand equation is Q equals 400 minus 10p. Find the elasticity of wool. Okay, so let's look. So part A. Let's first look at the effect on revenue. So if we have revenue at a price of $10, that's price times quantity. So 10 times 400 minus 10 times 10. So again, this is price times quantity. So that's 10 times 300. So that's $3,000 in revenue if we sell at a price of $10. If we raise the price of wool by $1, in this case we're going to get 11 times 400 minus 10 times 11. So 11 times, let's see, that's 400 minus 110, so that's times 290. So this equals 3190. So what does that tell us? Well, in this case, raising price, so raising the price, increased revenue. So in this case, raising the price actually increased the revenue. So now let's find elasticity. So elasticity of wool. That's going to be absolute value of price over quantity. This is at $10. So that's going to be 10. Oops. So 10 over 300 times the derivative. So the function for the quantity up here, its derivative, dq dp, that's just negative 10. And that's for any value of p, right? Because you just get negative 10. So this is negative 10. So we end up getting negative 100 over 300. So absolute value of negative a third. So that's just 1/3. Okay, or 0.33 approximately, which is less than 1. So we have that demand is inelastic here. Okay, so we have elasticity being less than 1, and we were able to increase revenue by raising the price, right? Because basically when the product is inelastic, that tells us we can raise the price further, and essentially our customers will go along with it, right? They'll be okay to pay a slight increase in price. Okay, so now let's look at part B. 300 units of houseplants are sold when price is $10. When the price of houseplants is raised by $1, what is the effect on revenue if quantity sold drops by 100 units? Houseplants demand equation is Q equals 1300 minus 100p. Find elasticity of houseplants. All right. So, So let's do this down here. So part B. All right, so let's look at the change in revenue first. So R of 10, in this case, it said 300 units are sold when the price is $10. So that's $10 times 300 units. So that's $3,000. Raise the price by $1. That's 11 times the number sold drops to 200. So that's going to be $2,200. So in this case, raising the price actually decreased revenue. Okay. So now let's look at the elasticity. Okay, so elasticity of houseplants. That's going to be price over quantity, so 10 over 300 times the derivative, okay, so that rate of change. So in this case, our dq dp, our dq dp, that's going to be just negative 100. Okay, so much steeper rate of change in this case, that's negative 100. So that gives us negative 1,000 over 300, okay, which works out to 10 over 3, or 3.3333, etc., which is certainly bigger than 1, which means the product at this price is elastic. Okay. And so this tells us kind of the same thing that the revenue just told us, that if the product is elastic, you don't want to be raising the price right now because it's already expensive enough that people are not going to continue buying it if you increase the price by 1%. And we saw that here, are going from 10 to 11, that's a 10% increase, and you lost $800 in revenue just by raising the price by that $1. So this really can help us identify, the best places to maximize our revenue, because you don't want to stop too soon, like in part A, because then raising the price you can actually make more money. But you don't want to go too far, like in part B, because then raising the price more is starting to lose you that revenue that you need as a company. Okay.